Here's the answer before the setup, because the number is public and hardly anyone looks it up. The International Energy Agency put the world's data centers at 485 terawatt-hours of electricity in 2025, 17% more than the year before. And in a report published on the 16th of April 2026, it expects that to roughly double by 2030 to about 950 terawatt-hours, or around 3% of all the electricity generated on Earth. AI is not all of that. It's the fastest climbing part, and the same report expects electricity going to AI-focused data centers to triple across those 5 years. So where does the power actually go? Into 3 physical, unglamorous places. A chip that pulls 700 watts. A building that spends roughly another half a watt getting rid of heat for every watt the chip burns. And an answer so cheap it looks free, which turns out to be the expensive part. Take the chip first. An Nvidia H100, the accelerator much of the recent AI boom was built on, has a thermal design power of 700 watts in its SXM server form factor. That's one of them. A serious training cluster holds tens of thousands, wired together, running flat out for weeks. 700 watts is about a microwave oven. The microwave stops. Training is where most people's imagination goes, and the receipts exist. Meta published a model card for Llama 3.1 with the compute written out. The 405 billion parameter version consumed 30.84 million GPU hours on H100 hardware. Multiply those hours by 700 watts, and you land near 22 gigawatt-hours at the silicon alone before a single fan turns. Meta's own accounting puts the location-based carbon at 8,930 tons. Market-based, once its renewable energy contracts are counted, Meta reports 0. Same run, same electrons, 2 published answers. Earlier runs cost less. In 2021, David Patterson and colleagues from Google and Berkeley published GPT-3's training bill, 1,287 megawatt-hours, and 552 tons of carbon dioxide equivalent. 10,000 V100 chips, grinding for 14.8 days in a Microsoft data center. Those are enormous numbers. They're also one-off numbers, and that's the part people skip. You train the model once. Then it answers questions for years, and at some point the answering quietly overtakes the building. Alexandra Sasha Lucioni, Yassine Jernite, and Emma Strubel did that arithmetic properly in a paper presented at the ACM Fairness Conference in Rio in June 2024. They worked with BLOOMz, an open model family whose training logs were public enough to reconstruct the whole life cycle, something almost no commercial system allows. Its 7 billion parameter version took 51,686 kilowatt-hours to train, plus another 7,500 to fine-tune. A single query cost about 1/10,000th of a kilowatt-hour. Break-even arrives at 592 million queries. That sounds like a wall you'd never hit until you check what these systems now serve. In February 2026, OpenAI said ChatGPT had passed 900 million weekly active users. So how much of the total goes to training and how much to serving? Hyperscalers rarely open their books on that. Google did in a 2022 paper where Patterson's team reported that across 3 consecutive years, about 3/5 of the company's machine learning energy went to inference and 2/5 to training. The authors called it the first disclosure of its kind by a company that size. Meta has published a partial breakdown of its own, putting inference at roughly 40% of the end-to-end footprint of one of its recommendation models. Beyond those 2, the industry has mostly stayed quiet. Training is the deposit. Serving is the rent, and the rent never stops. Which brings us to the number everybody fights about. What does one answer cost? In August 2025, Google published a measurement rather than an estimate. The median text prompt to its Gemini apps used 0.24 watt-hours, under 9 seconds of television, along with 1/4 of a milliliter of water and 0.03 of a gram of carbon dioxide equivalent. In the same work, and this is the honest bit, they showed what happens when you draw the boundary tighter. Count only the active accelerator, ignore idle provisioned capacity, ignore the host processors and memory, ignore the building overhead. Then sample your best utilized machines rather than the whole fleet. The identical prompt now reads 0.10 watt-hours. By Google's own comparison, the full figure is 2.4 times the narrow one. The prompt never changed. Only the fence around it did. Move the fence the other way, and you get other answers. Epoch AI's Josh Yu estimated a typical GPT-4o query at around 0.3 watt-hours in February 2025, roughly 10 times below the 3 watt-hour figure that headlines had been recycling since 2023. His caveats are more interesting than his headline, though. Hand the same model a 10,000 token input, and he puts it near 2.5 watt-hours. At 100,000 tokens, 40. A reasoning model, which thinks in tokens before it replies, produces about 2.5 times more of them. The lab measurements sprawl wider still. Lucioni's team benchmarked 88 models across 10 tasks and 30 datasets on identical hardware, and the spread between the cheapest and the most expensive came out above 1,400-fold. Sorting text into categories cost about 2 watt-hours per 1,000 queries. Generating images averaged nearly 2,900 watt-hours per 1,000, and the hungriest image model they tested burned 11.5 kilowatt-hours per 1,000 pictures, which works out at roughly half a phone charge for one image. A separate 2025 benchmark of 30 commercial models by Nidhil Jegam and co-authors found a 65-fold gap between the leanest and the heaviest, with long prompts on the worst offender passing 29 watt-hours. So when somebody hands you a single confident figure for what AI costs, that figure is a claim about a boundary, not about physics. Which model? How long the prompt ran? Whether idle machines get counted, whether the cooling does, whether anybody bothered to include the power station over the horizon. Every one of those choices moves the result by more than the result itself, and almost every viral number arrives with none of them disclosed. That's the tell. None of this has touched the building yet, and the building is where a surprising share of the electricity dies. The industry measures it with a ratio called power usage effectiveness. Total electricity into the site divided by electricity reaching the computers. A perfect facility would score 1.0. The Uptime Institute's global survey put the industry average at 1.58 in 2023 and 1.54 in 2025, which is to say it has barely moved in half a decade. Weight the 2023 number by capacity, so the giant sites count more, and it improves to 1.47. Google reports 1.09 across its own fleet. Put that plainly, at the average data center, roughly 35% of the electricity coming through the door never reaches a computer. At Google's, it's about 8. That gap isn't rounding, and it's decided by engineering choices a user never sees. What is all that overhead doing? Almost entirely, it's fighting heat. The IEA's breakdown gives servers about 60% of a modern data center's electricity, with cooling running from about 7% at an efficient hyperscale site to over 30% at a poorly run Enterprise 1. And underneath, that sits a piece of physics nobody argues with. The electricity going into those racks doesn't leave as anything else. Computation stores no meaningful energy, so essentially every joule that enters a data center exits as warmth, and the entire cooling apparatus exists to carry it outside before the hardware cooks. Strip away the language about intelligence, and a data center is a heater with opinions. There's one more variable, and the viral numbers never carry it. A kilowatt-hour is not a kilowatt-hour. Ember's 2026 dataset, published through Our World in Data, gives the carbon intensity of electricity country by country for 2025, and the spread is brutal. Norway at 28 grams of carbon dioxide per kilowatt-hour and France at 41, against a world average of 458, the United States at 384, Poland at 589, India at 670. Same chip, same prompt, same joules, and the emissions swing by a factor of more than 20 depending which side of a border the building sits on. Globally, the IEA finds coal is still the largest single source feeding data centers, at roughly 30%, with renewables at 27, gas at 26, and nuclear at 15. Where you put the warehouse matters more than almost anything the software does. Now the honest part, which is that the trajectory is genuinely unsettled, and the IEA says so in its own words. There is substantial uncertainty both about data center consumption today and in the future. Its 2025 analysis ran a base case and 3 sensitivity cases, and by 2035, the spread across them stretches from 700 terawatt-hours to 1,700. That's not a forecast with tidy error bars. It's a gap wide enough to hold 2 different worlds. The reason is a race between 2 curves moving in opposite directions at speed. Per task, energy keeps collapsing. Google measured a 33-fold drop in the energy behind its median prompt in 12 months, and the IEA's 2026 assessment reckons energy per AI task is falling by at least an order of magnitude a year. Meanwhile, the tasks keep swelling. That same report notes that newer applications, video generation and agents that run for hours, can consume hundreds or thousands of times more energy per query than a chat message. One curve is falling fast. The other is climbing fast. Nobody can honestly tell you yet which one wins. You can read the industry's own uncertainty in where it's putting money rather than in what it says. Capital spending by the big technology companies passed $400 billion in 2025, and the IEA expects roughly another 75% on top in 2026. Grid connections have become the binding constraint, so American developers are going around the grid entirely. Satellite tracking of the on-site gas plants they've announced shows about a fifth are already clearing land or under construction, and the IEA reckons 15 to 27 gigawatts of on-site gas could be feeding data centers by 2030. Orders for gas turbines jumped 70% during 2025. Nobody buys turbines because they think demand is about to flatten. So why does AI use so much energy? Per answer, honestly, it doesn't. A quarter of a watt-hour is a rounding error in your day, and that figure has been falling faster than almost any efficiency curve in modern engineering. The energy lives in the aggregate, and the aggregate is decided by choices made long before your prompt exists. Which site, which grid, which cooling design, which model gets pointed at which task. Route a question to a heavy reasoning model instead of a light one, and it can cost tens or hundreds of times more for an answer nobody needed improved. One last thing, though, because the whole argument keeps stepping over it. Every watt that enters those buildings comes back out as heat, and almost all of it is currently thrown into the sky above a field in Virginia or Iowa or County Dublin. Unmetered. Unsold. Finland already pipes that warmth into people's radiators. A data center buried under central Helsinki heats something like 500 large houses, and a scheme around Espoo is planned to reach 250,000 households. It's the rare part of this story with no technical mystery left in it at all. So the next time the energy question comes around, skip the argument about the prompt. Ask where the building is, what's feeding it, and where the heat goes after it leaves. The heat is the only honest ledger in the whole system, and right now we're paying for it twice.